Hello and welcome back. Over the last few lectures, covered computational number theory. That was the main tool to bring us to some novel and exciting, historically at least, cryptographic goals, namely the ability to do asymmetric cryptography. So today we're going to talk about how you apply all that number theory to do asymmetric encryption. This is a fascinating story how public key encryption and asymmetric encryption in particular were developed. You can read this book, for example, if you have some free time on your hands. It's a non-technical historical account. It talks about all the different people involved who were quite colorful characters. They're all well and alive today. You can go to cryptography conferences and meet them. So let's start by recalling the symmetric setup that we're going to change to an asymmetric one. So in that setup, when Alice and Bob want to communicate, the precondition is that they possess a shared secret key. That means they both have the same key and it's not known to the adversary. So consider some implications of this. If Alice now wants to communicate with a third party, then she needs another key shared with that third party distinct from this one. Also consider the effort required to acquire such keys. If Alice generated them, she must find some way to communicate them to her partners over private and authenticated channels. It's these kinds of problems that in the early 70s motivated the introduction of public key crypto. People wanted to simplify key distribution and simplify usage. And here's what they effectively dreamed about. The idea would be that Alice has a secret key. That key is private and personal to her. It's not shared with anybody, in particular not the person who is encrypting. However, something novel, this secret key has a public image, some kind of function of it that is in fact known to anyone. If you want to send Alice encrypted data, you only need her public key. You can grab that from some public space. For example, think of it just like a phone number that you look up somewhere or an email address that you find online, and you just somehow as a function of it do something, and you can create ciphertext which only Alice can decrypt using her secret key associated to that public key. So the differences between this and the symmetric setup are that senders of encrypted information, people who encrypt the Bobs and Charlies, don't need any secrets. They only need Alice's public information. Secrets are not eliminated, they do exist. Alice has a secret key, but it's private to her. It's not shared with anybody else. As with any new cryptographic primitive, we start with some syntax. Remember, syntax means if I want to give you a description of the scheme, what do I need to specify? And just like with the symmetric encryption scheme, an asymmetric one consists of 3 algorithms or 3 descriptions of algorithms, the key generation, encryption, and decryption ones. But the way they work is a little different. Key generation will be run by Alice to set things up, and it will return not 1 key like before, but 2. There's a secret key for decryption and then an associated public key, and these two have some particular mathematical relation that will be important for making the whole thing work. Now, when somebody wants to encrypt, all they need is this public key. As a function of that in the message, your encryption algorithm will produce a ciphertext. It can be randomized, and for good security, it will be randomized. The adversary will be eavesdropping, trying to take the ciphertext and figure out its content, at least for the considerations here, but at some point we'll also want to consider that it's able to modify these ciphertexts. At the other end, when the ciphertext reaches Alice, she decrypts, and this decryption is done using the prescribed decryption algorithm and the secret key that she generated earlier. And that will recover either original message or maybe our special symbol bot saying something went wrong. So anytime we see a public key encryption scheme described, expect to see code or pseudocode for these three algorithms. Before there's any consideration of security, we need, as usual, some kind of requirement saying that communication is maintained faithfully. We call this the correct decryption requirement. It just says that if you encrypt a message properly with the prescribed algorithms and keys, and then you decrypt, you will indeed get back the same message. So the requirement says that having fixed a particular scheme, it satisfies correct decryption if the following is true. Take any key pair that may have been generated by key generation. This means that these objects obey whatever mathematical relationship this algorithm puts. Now encrypt some message under the public key, get a ciphertext, and now decrypt that under the associated secret key, and you're required to get back the message. The probability being 1 is reflective of the fact that E may be a randomized algorithm, so it just says no matter what random choices E makes, this is always going to be true. Now, in specific schemes, this requirement will be true for messages in some message space associated to the scheme. And when we give the scheme, we'll usually say what this message space is. That reflects that schemes often restrict the space of messages or data that they're capable of encrypting, sometimes for algebraic reasons. So how does it all work? How do you set all this stuff up? Well, the first step is key generation, and that's something Alice does locally. So she gets on her computer and she runs some software, and that will generate a key, and she'll store the secret key. You can find such software readily. You can go to, for example, OpenSSL and get routines which perform this kind of key generation. Alice will then somehow allow anyone who wants to send her encrypted data to come into possession of her public key. There are many mechanisms required to make that happen. At the level of encryption that we're studying here, we won't worry about that. So our assumption is going to be that Bob, as a sender, has acquired Alice's public key. And once that happens, the sender can simply encrypt under it, produce ciphertext using our encryption algorithm, and if Alice gets those ciphertext, she can decrypt. In all of this, we will not require privacy of the public key. That's a big change relative to the symmetric setting, but that doesn't mean that there are no security requirements on it. It is required that that authenticity holds, in the sense that when a sender gets something that it thinks is Alice's public key, it really should be hers and not someone else's. We'll see later many different ways to enforce that. The most popular is certificates, but other ways could be some kind of trusted databases, like, for example, PGP does. But again, at the level of this chapter, where we're studying the encryption primitive, we're simply going to assume that this public key is properly distributed. So now that we have a syntax, the next step, of course, is to ask what's the security requirement. We have not yet given any examples of these objects, but we are studying them abstractly, and before we can evaluate examples, we'd like to see at least what we want in terms of security. It turns out that encryption security is not a priori a simple thing. It takes work to come up with a good definition and to understand what privacy really means and what the requirements should be. But luckily for us, we've already done that work in the symmetric setting, where we defined IND-CPA. And we're just going to adopt the analogous extension of that to the asymmetric setting. So we will be able to state the definition quite directly and quickly, And we'll see only one really major change, which is that the presence of this public key, and we are going to reflect in security that really is public, so the adversary also knows it. And with that, we'll just give the games. So by now you've seen lots of these games, so hopefully it's not daunting to see these. And they look very similar to the IND-CPA games for symmetric encryption. So to do it completely, we fix an asymmetric encryption scheme, the three algorithms of the form we just saw in prior slides. As usual, this is a public object, which means everybody knows how the algorithms work, and you can assume the adversary has code to execute them. There are two games, left and right. They differ very, very slightly. The only place they differ is one bit, a 0 here and a 1 here. Both of them begin with an initialized procedure, which runs this algorithm over here to get a public key and a secret key. Remember, this algorithm returns this pair of mathematically related keys, not as in the symmetric setting, just one key. Here's an important change from the symmetric setting. There's a return statement. The return statement means the adversary gets us input this public key, and that's what reflects that it's in fact public. There is no such statement for symmetric encryption. The right game has exactly the same initialized procedure. This procedure is executed once, and now these keys are fixed, at least internally, to the game. The exported procedure is again called left or right. The adversary can call this as often as it wants. And the arguments it must provide is a pair of messages, not one message, but two, and they're required to be of the same length. Now, what the games do is that they run this encryption algorithm with this public key to encrypt a message, and the only difference with the games is in the left message is chosen, in the right message is chosen. This reflects that encryption may be randomized. Every time you encrypt, it picks fresh coins. So even if you twice encrypt the same message, you wouldn't get back the same thing. Okay, so now the adversary goes to this left or right oracle, makes queries, it can ask whatever messages it wants, it can do so adaptively, and then it eventually decides, okay, I think I know whether you're encrypting the left or the right message. I think I know which game I'm playing. And it will output a 1 to indicate I think I'm in the right world, and a 0 to indicate I think I'm in the left world. As usual, we're not interested so much in the actual magnitude of the probabilities of returning 0 or 1, but in how close they are in the two games. If we run the adversary with the game in the left case, this is the left game executed with the adversary, it will return either 0 or 1, and there's some probability it returns a 1. So that's this number over here. Now take the same adversary, run it with the right game. Again, the adversary's output is a 0 or 1, and there's some probability that that bit is a 1. And that's this object over here. What we're interested in is how far apart they are, and that's captured by the advantage defined as the difference between those probabilities. We call it the IND-CPA advantage. Just as for the symmetric setting, you'll always know whether we are in the symmetric or asymmetric one just from the syntax. As usual, the advantage is superscripted with the name of the metric, subscripted with the object whose security we're measuring. Here the scheme, and as argument has the adversary, and the advantage of course changes as you move across different adversaries. This simply repeats stuff that I've already said, just so you can have it in writing, and also highlights some of the main differences and novelties compared to the symmetric setting. One of those is that the return PK statement initialized means the adversary gets the public key as input. Of course, it doesn't get the secret key, otherwise it could just decrypt and there'll be nothing interesting to say here. Remember that you can only call the left or right oracle with equal length messages. If you use messages of unequal lengths, your adversary is simply invalid, and its advantages are either undefined or just 0. Remember that encryption can be randomized. It's a good exercise to go back and see that if encryption was deterministic, it would be very easy to violate this security definition. Okay, so we now have our target. We need to build some scheme meeting the syntax and security properties we've just defined. And how do we do that? Well, we already know that if we were to try to merely use symmetric techniques like block ciphers, we wouldn't get very far. So it isn't for nothing that we studied number theory. We've been hinting all along that we're going to need number theory in some crucial way to make this happen. So let's give it a try. What do we know from the number theory? We know that we saw as a hard computational problem that of computing discrete logarithms in a cyclic group. So let's say we fix a public cyclic group, G. We let little g be a generator, also public. And we know what that means, that every element in the group is some power of little g. Now, since the discrete log problem is assumed hard, the way we expect to leverage this is that the adversary's task in violating security of encryption should somehow come down to computing discrete logs. So that would tell us that this adversary is unlikely to violate the security of the encryption. So here's a natural way to set it up. Why don't I encrypt x as g to the power x? So we let x be the message, it's now an exponent, and let g to the power x be the ciphertext, which is a group element. We can compute this easily using our mod x algorithm. Why have we done this? Because if I hand the adversary this ciphertext and say, what was my message? It's going to have a hard time figuring that out, right? Because that is exactly the discrete log problem, go from g to the x to x. So it looks fairly promising. Does that work? Are we done? Well, a little thought says no. In fact, the difficulty here is that not even before we even get to security, is that we don't even really have a proper scheme. In particular, we've never said what the secret key is, and there seems to be no way to decrypt in this scheme. How is the legitimate receiver going to recover little x from g to the x? It has to have a fast way to do that, much faster than taking discrete logs, and for this scheme, I don't have any way to give that. In fact, and the description was in any case incomplete because I didn't really say what any of these keys were. So we need to think about it a little more. And it turns out that the discrete log problem doesn't lend itself to public key encryption, but something very close does, which is the computational Diffie-Hellman problem that underlies the Diffie-Hellman secret key exchange. So we're going to go back to that key exchange and see how we can quite readily turn that into a public key encryption scheme. They're different because secret key exchange tries to solve a different problem. How do Alice and Bob come into joint possession of a symmetric key? And it allows parties to send messages back and forth. But the math underlying them is very similar in the end. So let's recall that in the Diffie-Hellman secret key exchange, there was a large public prime and a generator of the group of integers mod p, at least for this selection of groups. Alice picks a random exponent. The exponent will lie in zp minus 1, so it'll be a number between 0 and p minus 2. Why is that? Because the group has order p minus 1. She then raises g to the power x mod p via our mod x algorithm to get big X and sends that over to Bob. Bob likewise picks a random exponent y, raises g to the power y to get big Y and sends big Y over. The shared key is this quantity here, g to the power little x little y. All these computations, of course, being modulo p, since that's the group we're working in. The trick with Diffie-Hellman is that this can be seen either this way or this way. If you look at it this way, it's something that Bob can compute from big X and little y. looked at this way, it's something Alice can compute from big Y and little x. And so that's how they get a joint key. And we've decided that it's hard for an adversary to find this key because doing so would require solving the computational Diffie-Hellman problem. Okay, but now what we want is a public key encryption scheme. So we have a different syntax. We have our key generation, encryption, and decryption algorithms. We have elements that don't enter here at all. We need public and secret keys. None are present here. We need to encrypt a message. There's no message here. So how do we bridge all those gaps? It's actually quite simple. What we do is we think of Alice's choice of little x as her secret key. And the flow she sent to Bob, the big X, which is due to the power little x, think of that as our public key. So that's our keys. Now, the process of Bob sending something to Alice is effectively going to be turned into encryption. What Bob does is if he wants to encrypt a certain message for Alice, he already knows Alice's public key G to the X. So the first step in the Diffie-Hellman protocol is effectively done. He has G to the X. So just like in the protocol, he picks a little y, and imagine that he sends big Y, which is G to the little y, to Alice. If that's the case, then both of them are in possession of this quantity here. So even before Bob actually transmits G to the y, he knows that if Alice gets it, she would know this. So what he does is he encrypts the message under this. How do you do that? Well, you encrypt using some symmetric scheme, because in the end, both parties will have this object. So what he transmits then is G to the y and a ciphertext encrypting the message under this. What does Alice do? She recomputes this, that's the Diffie-Hellman part, and then once she has that, she will decrypt this ciphertext here using this as the key. That was a symmetric ciphertext. The recomputation here is done as in the Diffie-Hellman key exchange. She has the little x, that was her secret key, and this was simply present in whatever Bob sent her. So we'll see this in more detail, but as this idea shows, we kind of bootstrap symmetric crypto to get asymmetric, because this part here is actually symmetric. So in some ways, the role of the number theory is to exchange a key. So here's a pseudocode description of a scheme that emanates from the prior description, intuitive description. So we fix a group, cyclic group, let M be its order, let G be a generator. We'll also need a hash function. The hash function has to map group elements to strings of some length k. The hash function is public, and you should think of k as your message length. So whatever is the length of the data you want to communicate. And now we have a scheme. It's called DHIES, for Diffie-Hellman Integrated Encryption Scheme. And as usual, to specify it, I have to tell you three algorithms: key generation, encryption, and decryption. The message space is the set of all strings of length k. How does key generation work? It does what Alice did in the secret key exchange. So it picks a random exponent little x, and that will be drawn from the integers mod n. Now in our key exchange, we had assumed that the group was ZP star. This description is more general. It's for any cyclic group. If the group is ZP star, then M would have value P minus 1, which would match the Diffie-Hellman key exchange. But in general, it's just the group order. She then computes big X, which is due to the power little x. And she returns this pair. So this is the public key, this is the secret key. Remember, that's the formal output of the algorithm. What happens next in the usage is that Alice holds on to the secret key, and we are assuming that the public key is somehow magically communicated to Bob to encrypt with. So how does Bob encrypt? He has to, this is the description of the encryption algorithm. It takes Alice's public key big X and a message M that's a k-bit string. It starts by doing what Bob would do in the Diffie-Hellman key exchange. You pick a random exponent little y, raise g to that power to get big Y, and then you compute what would be the shared key in the Diffie-Hellman key exchange. You take Alice's public key big X and raise it to the little y, and that's this value over here because big X is g to the little x. What does Bob do with that? He treats it as a symmetric key in some sense. So he hashes it with the hash function that'll give out a k-bit string. This is a group element, and the inputs to the hash function are group elements, so that matches up. And then simply masks the message with that. So the idea is this is like a pad, a one-time pad type thing, and you XOR the message into that. What does the ciphertext return? It has two components. One is this g to the y over here, and the other is this symmetric ciphertext w over here. So that's what Bob sends across to Alice. Now, how does Alice decrypt? She receives this ciphertext, it's this pair, and she has access to her secret key little x. We know that W looks like this, and Alice wants M. To do that, she's going to first find out what K is. Once she has K, she can always recover M by this formula over here. That's simple enough. How does she get K? Well, that's what the Diffie-Hellman key exchange tells you. It says that if K is this, which is this, it can also be written like this. So since Alice has big Y and little x, she can compute K. And that's it. That's our scheme. Now, a couple of clarifications about this in case you start seeing instantiations. And I hinted at this a little bit before. This is written in the case where we have a general group. If you are looking at a specific group like ZP star or integers mod n for some n, let's say ZP star an example, then you have to interpret everything accordingly. So M will be the group order for ZP star, which is P minus 1. G to the X will be G to the X mod P, and you would compute it with your mod X function. This computation would be mod P, so with this one, and so on. So you can hopefully make these mappings as necessary. Well, what about security? Well, we have our target. We know that we want to think about IND-CPA as the goal for these symmetric encryption schemes. And to cut a long story short, this scheme is basically good under appropriate assumptions on the primitives. So if we assume computational Diffie-Hellman is hard in G, which we've defined in prior chapters. And we also assume something about the hash function. Clearly, our lousy hash function is not going to work here because then even given W, you might learn something about M. But in practice, they usually do something like this for the hash function. They would use some cryptographic hash function like SHA-256 and instantiate H with that. Except that this one returns 256 bits and maybe your message is longer. So you want more than 256 bits out. How do you get that? You take your input and maybe you hash little perturbations of it. So prefix with a 0, then with 1 and so forth. And by such techniques, you can get out lots of bits. From a theoretical perspective, the proof that this is IND-CPA requires that H is what's called a random oracle, which is a perfect hash function. It has random behavior. That's not something we're going to formalize in this class, but we would do that in a graduate class. So in practice, as we've seen before, the preferred group in which to work when you're doing Diffie-Hellman or discrete log-based crypto is elliptic curve groups. Now, we haven't said what they are mathematically, but it doesn't matter because they're just groups and we know what the group abstraction means. And we saw that the prior scheme could be defined in an arbitrary group. And so the elliptic curve integrated encryption scheme is something like what we saw with the instantiated in elliptic curve. When that happens, you get quite high performance. So encryption will be 2 exponentiations. If you're looking for, say, 80 bits of security, you can use a 160-bit group. And so the costs are two such exponentiations for encryption, one for decryption. And the ciphertext is just 160 bits longer than the plain text. So that's good. So we have now achieved discrete log or computational Diffie-Hellman based encryption. This is a popular and well-known scheme, and you now have that to play around with. This little exercise takes you through a slight variant of the scheme. It allows you to play with the algebra so that you can see how you would perform decryption in this scheme. And next time we'll look at this.